Alright, now we're going to go over something called Hess's law. So let's take a simple reaction like this. Carbon converts to carbon. Now, the difference being we're basically going from diamond to graphite. So yeah, probably the rocks that you use as gravel on your driveway converts to pencil lead. Now, before you guys get concerned about diamonds naturally turning into pencil lead, before you rush to your family vault, do not worry, your diamonds are not turning into graphite before your very eyes. This actually takes a very long time. We're talking about like a very long time. We're talking millions of years. So, how the heck do we measure the enthalpy change if it takes too long? It's just such a slow reaction. How can we figure it out? Well, luckily, there's a law that we're going to take advantage of. This law is actually very simple. Basically, it says that if we have a couple of reactions, we can add them together, and we can add their delta H's. And I know that sounds confusing, so let's go with an example. Let's say we have something like this. So let's say we had these two reactions. If we added them together, your reactants for each of the reactions would become your reactants for the overall reaction. So we've got A plus B plus C plus D yields, and then your products on both of the reaction become your overall products over here. So we get we get yields F plus 2E. So the idea is that if we know the delta H for two reactions, if we were to add up the reactions and we got a brand new overall reaction, how would we find the delta H? Simple. Just like we added up the reactions, we can add up the delta H's. So 5 plus 10 gives us 15. That's Hess's law. Now obviously it's going to get a little bit more complicated, so let me give you another example. What if we had something like this? 2A plus B yields C, and our delta H is 10 kilojoules. And we have another reaction. C plus D yields 3F. And our delta H is a negative value, negative 5 kilojoules. Okay, well, if we were to add them up, our new overall reaction would be 2A plus B, because we got those reactants there, and then we have reactants here, plus C plus D yields, now we have our products, we have C plus 3F. Well, what's nice about Hess's law, or what we're going to take advantage of, is this. If you have something that shows up on both sides exactly the same, I'll underline it in red so you can see. In this case, we have C coming out exactly the same. It's similar to the spectator idea, but it just has a different name. It's called intermediate. So basically, it's a substance that gets produced in a reaction, but then it gets used up a little bit later before the final reaction's over. So it doesn't come out in the overall reaction. So what we do is we erase it. We cancel it out. So remember, we had placed it there before, but we're just going to go ahead and remove it. So we don't write it in the overall reaction. So the overall reaction is this. 2A plus B plus D yields 3F. That is the overall reaction when we add two reactions together. And what's the delta H for this? Well, we add them up. 10 plus negative 5 is 5 kilojoules. So it kind of sets us up to solve this problem. If we want to find delta H for this reaction, it helps if we can find a couple of reactions that we can add together to give us that reaction. Because if we know the delta H's of the reactions that we added to get this reaction, we can add the delta H's to get the delta H we're looking for. So here are the two reactions that we can use. In the first reaction, we've got diamond burning up to form carbon dioxide, and we know a delta value for that. And in the second reaction, we have graphite burning up to form carbon dioxide, and we have a delta H value for that. So Hess's law says that we can add reactions and add up their delta H's. Now we have one tiny problem. If we add up this reaction right now, our reactants are going to be carbon diamond plus carbon graphite, and that can be kind of misleading. I put the D for diamond, that's graphite, plus there's two O2s, so we can put them together, two O2s, yields, and there's two carbon dioxides. And our problem is that nothing cancels out. And this reaction right here does not look like the reaction that we want. So, how do we solve this problem? Very good. The law of conservation of mass. We know that we want diamond on the reactant side. So that's good, that's perfect. We don't want O2 to come out, we don't want CO2 to come out, which means they have to cancel each other out. They have to show up on both sides of the reactions so they can get rid of each other. Graphite is our problem. It is not on the side that we want. We would much rather have this the other way, flipped. So instead of having graphite plus O2 yields CO2, it would be much better if we had CO2 breaking down into carbon graphite plus O2, because that would get rid of this reaction. We wouldn't use that one. We would be using this new updated reaction. And if we added the two reactions together, our overall our reactants are going to be carbon diamond, oxygen, and carbon dioxide. And our products would be carbon dioxide, carbon graphite, and O2. So if we went ahead and add them all up, we would get carbon diamond plus O2 plus CO2 yields, so we took care of those, and we'll do our product, CO2 plus carbon graphite plus O2. And obviously we don't want substances that come out on both sides, so carbon diamond is fine because there's no carbon diamond on the product side. O2 gas, they're going to cancel each other out. CO2 gas, they're going to cancel each other out. Carbon graphite, that's not on the reactant side. Even though it's carbon, it's a different form. So states of matter and types of material does mean something here. So here we have carbon diamond turning into carbon graphite, which is exactly the reaction that we want. All we had to do was manipulate one of the reaction that's given to us. which you're going to have to kind of get comfortable doing. Manipulating equations if, when we add them up together, they don't come out the way we want them. But there's a little problem that we have to solve. When we change this reaction, what's the delta H for it? It's not the same. It's not negative 393.5. Like we said earlier, thanks to the law of conservation of energy, you should be able to figure it out. If we think about the energy diagram, the delta H for graphite reacting with oxygen turning into carbon dioxide is negative 393.5 kilojoules. That means that we're going from reactants to products, and we are releasing a bunch of energy. So that value being the 393. Well, the reverse reaction is going to be the same amount of energy that was released to go from the graphite and oxygen to the carbon dioxide. Therefore, the reverse reaction is going to be the same magnitude, but opposite sign. So it's positive. So it's positive 393.5 kilojoules. And since we added these two reactions together, this one and this one, we can add these two delta H values. So negative 395.4 plus positive 393.5 comes out to a delta H value of 1.9 kilojoules. So that's usually the point of Hess's law. You basically have a target reaction that you are trying to find the delta H value for, and you have 1, 2, or 3 little reactions that I'm just going to make up stuff, just blah blah blah. And you basically have to be able to either add them all up and get the reaction that you want, or it turns out that it doesn't come out so convenient, right? So you got to be able to manipulate equations. So let's go ahead and do a practice for you. Say you had the reaction lead-2 chloride react with chlorine gas to produce lead-4 chloride. And your two reactions given to you to use are right here. So this right here, that is our target equation. That is what we want to add our reactions together to and get when we do that. Now, looking at your given reactions, you should scope through them and figure out, okay, who's in my target equation and who's not. So for example, you see PBS solid. Well, PBS solid is not in our target equation. What that means is, at some point, that's going to have to get canceled out. In order to get canceled out, it has to appear on both sides. That means it's probably going to show up somewhere else on my given equations as well, and it does. That's a major hint that one of these is most likely going to have to be reversed. Now, I see Cl2 in my given equation, and it's also in my target equation, which means I'm going to ultimately want to have one Cl2 on the reactant side, but two show up on this side, so that could be a potential problem. I see PCl2 solid showing up, and PCl2 solid is on my PbCl2 is on my reactant side, and this is on my product side. More than likely, this is going to have to be flipped. I see PbCl4, PbCl4. So this is the general strategy that's used when we're trying to use Hess's law to find the delta H of a reaction. Start from the very beginning. The very first substance we have in our target equation is PbCl2 solid. States matter. So we need to find PbCl2 solid, in our given reactions, and it's located right here. You have to ask yourself two questions. Is it on the side that you want, and is it the coefficient that you want? So let's ask ourselves, PbCl2 solid, is that on the side that we want? No. Is it the coefficient that we want? Well, the coefficient here is 1, the coefficient here is 1, so yes. So anytime we're in that situation, it should be obvious. This reaction needs to be reversed. And because of the conservation of energy, we know that when we reverse it, the only thing that changes is the sign of delta H. It flips. Reversing any reaction flips the sign of delta H. If it was positive, it becomes negative. If it was negative, it becomes positive. Alright, so reversing the reaction gives us this right here. We flipped it. Our reactants became products, and our products became reactants. So the question is, what happened to the delta H? Well, remember, reversing a reaction flips the sign. So our new delta H is going to be positive 359.4 kilojoules. And now our PbCl2 is on the side that we want with the coefficient that we want it. So we're just going to go ahead and put a star right here by number 1 because we're most likely not going to manipulate that reaction anymore. It's just where we want it. Then we move on to the next substance, Cl2. Well, Cl2 shows up in two places. So I'm actually going to scratch this off because we changed it, so this reaction doesn't mean anything to us anymore. Cl2 shows up in two places. It shows up here and it shows up here. Now, although this doesn't seem ideal at first, what's nice is remembering if it shows up on both sides, it can cancel out, but we pay attention to the magnitude. On the reactant side, we have 2, and on the product side, there's just 1, which means only 1 is going to get crossed out, leaving 1 on the reactant side, which is what we want. So that's ideal. So the general rule is this. If a substance shows up on multiple places, put a question mark over it, and we'll come back to it. Usually, these problems will solve themselves. We took care of PbCl2. Cl2 we're going to hopefully solves itself. And now we'll move on to PbCl4 liquid. Well, PbCl4 liquid shows up right here. And it doesn't show up anywhere else. So we ask ourselves the two questions. Is it on the side that we want? Yes, it is. Is it the coefficient that we want? Yes, it is. In case you weren't sure what that meant, is it on the side that we want? Here it's on the product side. So we check to make sure that it's on the product side in the reactions that are given to us, and it is. So since this reaction in number 2 is on the side that we want, and it's the coefficient that we want, more than likely we're not going to manipulate this one. Well, we only have 2 reactions to play with, so if we can't manipulate anymore, we should go ahead and add them up, and hopefully it comes out to what we want. So let's go ahead and add these 2 reactions together. So here's our overall reaction when we add up these 2 reactions together. So we've got 1, 2, 3 substances on the reactant side of all the equations, and they're right here, 1, 2, and 3. It doesn't matter the order that we put them in. On the product side, we've got 1, 2, 3, and here they are, 1, 2, 3. So now we have to go ahead and simplify them. And what I mean by simplify them is check if anything shows up on both sides. If it does, cancel them out. So if we look at it, if we look at the first one, we've got Pb solid. Is Pb solid anywhere on the product side? Yes, it is, right here. So that is going to be canceled out. Move on to Cl2. Does Cl2 show up on the product side? Yes, it does, but only one of them. And over here there's 2. So what's going to happen is Cl2 is going to cancel out, and only one of the Cl2s is going to cancel out. That's my baby. He's finishing his avocado. Now we look at PbCl2. Does PbCl2 show up on the product side? No, it doesn't. So that's good. Does PbCl4 show up on the reactant side? No, it doesn't. So we're left with 3 substances in this reaction. We have Cl2, PbCl2, and PbCl4. And if we look at our target reaction, here it is, PbCl2, Cl2, and PbCl4. Since this is the reaction that we want, how do we find the delta H? Very good, you guessed it. You go ahead and add the 2 delta H's from the reactions. Notice that we had to manipulate one of them. So whenever you do these reactions, you can't just add up all the delta H's. You have to see if any of them have to be manipulated first. So once we manipulate the ones that we have to, and we lock down the reactions, we go ahead and add up our delta H's. So what is negative 329.2 kilojoules plus 359.4 kilojoules? Well, it comes out to 30.2 kilojoules, and that is your answer. So you kind of have to do some creative thinking when you're and problem solving when you're trying to use Hess's law. The main idea is before you can actually calculate delta H, you have to manipulate other equations, and there are two ways that you can manipulate them. One we already mentioned. One way that we can manipulate them is this: reverse them. When we reverse reactions, our reactants become the products, and our products become the reactants. The only thing that changes for the value of delta H is the sign, so that becomes negative 10 in this example. That's one way to manipulate them. The second way, sometimes you're going to have to be creative about it, but this works. It's actually pretty simple. You can multiply a reaction, which we've done before. When we were trying to balance things and we say, oh, if you get a 0.5, double everything, you can do it to a reaction as well. So that's kind of when I said, okay, two questions that you ask yourself. Is it on the side that you want, and is it the coefficient that you want? Let's say in your target reaction you wanted 2a, but in the equation that's given to you, your coefficient is 1. Well, what you're allowed to do is multiply the entire reaction. And if you multiply the entire reaction by 2, then your reaction becomes 2a plus 2b yields 2c in this example. Well, then how does delta H change? Take a guess. Very good, you guessed it. It doubles. So this gets multiplied by 2. And 10 times 2 is, I'll give you a second. Very good, 20. Now let's say your target equation, let's say somewhere in your target equation you wanted 3a on the product side. For whatever case, let's say D yields 3a. Let's say that was your target equation. And this was one of the many equations that were given to you to play with. And let's say A only showed up in one place, so this first one. Well, you would ask yourself the two questions. You would say, is it on the side that you want? And the answer is no, which tells you you're going to have to reverse this reaction. And then you ask yourself, is it the coefficient that you want? And the answer is no, because in your target equation you want 3, and this coefficient is 1. So what would you do? Very good, you guessed it. You would multiply this reaction by 3. That would give you 3a plus 3b yields 3c. And your delta H would also be multiplied by 3. So your new delta H would be 30. But it needs to be on the product side. So we still need to reverse this thing. So this turns into 3c yields 3a plus 3b. Well, how does delta H change? Very good, you guessed it. The sign flips, negative 30 kilojoules. So you guys are going to have some problems to practice. You're going to have to manipulate. In some cases, you only have to reverse. In some cases, you don't have to do anything. In some cases, you just have to double or triple, or you can multiply by 1/2 as well. And in some cases, you have to reverse and multiply. So good luck with your homework.